quick introduction to tree data structures. So what is a tree data structure? A tree data structure is a hierarchical structure that's used to represent and organize data in a way that's easy to navigate and search. It's not a non-linear data structure. It's faster to search for data than a linked list and an array, and it organizes data better than a linked list and array. All right, so here's a diagram for the tree data structure. Right here, we have our root and our key. And from the root, you can see it splits the nodes into separate trees. It splits into the left subtree and the right subtree. All right. And you can see right over here, we'll go B is the parent, D is the child of B, and E is the child of B, and D and E are siblings. And you can see right over here, this could be represented as a subtree. Also, we have leaf nodes. Leaf nodes are nodes that do not have any children. And the edges are what connects the nodes. All right. And if you want to get the height of a tree, we count the levels. So starting from the root node, we count at level 0, level 1, right over here, level 2, level 3, level 4. And if we want to get the height of a tree, the height of the tree is 4. All right. And between the root and the leaf nodes, between level 1 and 3, we call these internal nodes. All right. And we're going to go into the next slide. So we're going to go into binary trees. A binary tree is a data structure where each node at most has 2 children, and we could refer it, and it's referred to the reference is referred to the left and right child. The child's, so for example, we have our binary tree right over here. We have a node, and the most nodes a binary tree can have is 2, and the left child is 7, and the right child is 9 for 1. And you can see 5 is a leaf node because it has no children. 2 is a leaf node, it has no children. All right. And then we could represent a binary tree in an array. A is the array over here. Okay, we have our root node. We insert it at 0 index, and we want to insert our left node. So what we do to insert our left node is 2 times 0 plus 1, which is 1 over here. We insert 1, and then if we want to insert 2, we go 2 times 0 plus 2. So 2 times 0 is 0 plus 2. So we just put 2 here. This references this formula reference the right node, and this formula right here represents the left node. All right, and this is how we create a binary tree in an array. All right, so a strict, you can also call it full binary tree, a strict or full binary tree. A strict binary tree is a type of binary tree in which every node exactly has 2 children except the leaf nodes. So this is a perfect example of a strict, or you could say full binary tree. You could see right over here that 2 has 2 children. 1 has 2 children, 1, 2, and 3. 3 has 2 children, 6 and 7. 4 is a leaf node, and 5 has 2 children, 8 and 9. And you can, so 4, 8, 9, 6, 7 are leaf nodes, and 2, 3, 5 are internal nodes, and 1 is our root node. And this is a representation of a strict / full binary tree. All right, a complete binary tree is in which every level of the tree is completely filled, except possibly for the last level, which is filled from left to right. So if there's any, right here, you can see this is a complete binary tree. If there's any trees missing from left to right, so any branch is missing, let's say 2 from left to right, it's not a complete binary tree from here. So this is the left tree, and this is the end of the right. And you can see in between them, there we have nodes. So 4 is our left, and 6 is our right, and between them there's no nodes missing, so therefore it makes it a complete binary tree. 4 is our leftmost node, and 7 is our rightmost node, and you can see between them there is a node missing on 3's left child, so therefore it's not a complete binary tree. All right, a perfect binary tree is in which the interior nodes have 2 children and all leaf nodes are at the same level. So the leaf nodes, you can see over here, 4, 5, 6, 7 are leaf nodes, and 2 and 3 are our internal nodes, and our internal nodes have 2 children, so it meets the one requirement for a perfect binary tree. And 4, 5, and 6, and 7 are at the same level. If we count from the right side, the height, so we go 0, 1, 2, 0, 1, 2, and you can see from the root node, both levels are the same. You can say, or you can say that both levels, you can determine it for perfect binary tree, the root of both levels are the same on left side and the right side, or you can say, determine it if all the root nodes are at the same level. All right, and here is a diagram comparing a full, complete, degenerate, and perfect binary tree. All right, as you can see here, this is a full binary tree. We have all the non-leaf nodes have 2 children. As you can see, 4, 5, 3 are leaf, 2 and 1, 2 is the internal, and 1 is our root. And this is a complete, because from left to right, there are nodes. There's no nodes missing. And degenerate, you'll see this in. You can see this in probably in a binary tree or BST insertion, when we have no, it goes 1, 2, 3, 4, and it doesn't become a tree. It becomes more like a linked list, and its time complexity is O and N time. And you can see this is a perfect binary tree right over here. So you could see that the internal nodes have 2 children, and the leaf nodes are at the same level. All right, and let's go into binary search tree. So basically, a binary search tree organizes data better than a binary tree, but a binary search tree is a binary tree. It just organizes data. So what I mean, it organizes data better is a binary search tree. So let's say it puts the key, we say we have a node and we have our key, right? It puts the value that is less than that key on the left side of the node, the left child, and the value greater than the key on the right child. Okay, good way here. So this is a representation of a binary search tree. As you can see, the node here is 8. The node for the root node, and the key is 8. So anything less than 8 is put onto the left side, and anything greater than 8 is put onto the right side of the subtree. As you can see, and same applies for 3. So anything greater than 3, we put on the right side, and anything less than 3 put on the left side. And we keep doing this. 6 goes on to the, so Anything greater than 6 goes onto the right side. Anything less than 6 goes onto the left side. And we keep repeating this until we get our binary search tree. All right. And so we have the time complexity of a binary search tree. And let's say we're going to do insert 40, 20, 30, 60, 50, 10, 70. All right. Over here, as you see, we have a perfect binary tree. It's balanced. So if the tree is balanced, it would go into its average case. The search and the insertion will be log of n time. But if we go 1, 2, 3, 4, 5, 6, 7, we insert in this order, right? We're going to get something like a linked list, and we hit our worst case if the tree's imbalanced to O and N time. It's basically a linked list. So how do we solve this problem? We use self-balancing trees. So the self-balancing binary search trees. We have self-balancing binary search trees are AVL, which balances itself by its weight, the number weight. So by its left side and right side, and then we have red and black trees, which balance itself by colors. We're going to get more into them in the next lectures. And you can see that for AVL and red and black tree, the time complexity will, for best case and worst case, will be log and n time for insertion, search, and deletion. All right. What is this doing here? Okay. So, okay, and now we're going to B trees. B trees is a self-balancing tree data structure that can store multiple values per node, and is designed to reduce the number of disk accesses required to locate a particular piece of data, making it efficient for use in a file system and database. So basically, a B tree can have, as simplified, can have as many children as it wants. It's not limited to 2 children like a binary tree. And it's used, this is used in your databases or file system applications. We're also going to go into B trees in the future lectures. All right, and I want to thank you guys for watching this video in introduction to binary into tree data structures. All right.